Hi, I'm Russell Fox, and today I'll be talking about the prototype review for a course that I'm taking at the University of North Carolina, Charlotte. And the project name is the Clothing Dryer Efficiency Profile and Improvement. A faculty mentor is Dr. Scherer, and my lab partner is Jason Bilk. Today I'll be talking about the project requirements, the timeline, dryer test set / results, the conceptual circuit testing results, prototype design and description and drawing, the prototype hardware, block diagram, schematic and picture, the prototype software configuration and block diagram, the budget / bill, the safety provisions and standards, and the summary. Requirements. So the first requirement is to design a test set, and this test set is driven by LabVIEW, and it's ran on a personal computer, and that personal computer uses a data acquisitions card to collect voltages from 4 different sensors, one being a current transformer, the other one is an airflow sensor, and then the next one is 2 sensors combined, which is relative humidity and temperature, all in one sensor. And then that test set collects these variables and stores the data and allows the tester to go back and look at the data and analyze it. So that was the first requirement. The second requirement is to find a common dryer and a standard of wet clothes to perform testing on. That way it's a standard across the board and your data will have correlation because you're testing the same thing. We have to analyze the data. By analyzing the data, we're trying to figure out when the clothes are dry. That's the main action item of the third requirement. The fourth requirement is to design improvements. That is to figure out what exactly we need to do better to make the system be able to indicate when the clothes are dry. The fifth thing is to design a clothing dryer efficiency module, CDEM, well, I like to call it. It's a prototype right now. And the sixth thing is to test the prototype design, and seventh is to document the entire process. To kind of give you a heads up of where we're at, we're on number 6. So we're moving right along. Here's the NAT chart of where we were from day 0, which was in January, to 350 days, which will take us to the end of this semester, and it's all accounted for in here. And the prototype testing is where we're at, so we're right where we need to be. The dryer test set journal description. Again, it measures current, relative humidity, temperature, and airflow. So here's an example of that data that we collected in the test set. Red being the relative humidity, blue being temperature, and green being current. So this is one cycle of drying clothes. And as you see, the relative humidity goes up and then comes back down. The temperature steadily rises and eventually cuts off. And then the current, you see it cycling here, and that's the internal workings of the dryer, because when it gets too hot, the dryer has an internal circuit that cuts the heating element off for X amount of time. So basically, let me go back here. When we performed all these tests on different loads of clothes, we had a blended load of clothes, which consisted of shirt, jeans, and various clothing items. And then we had a cotton load, which consisted of all cotton fibers. And we performed various tests on them in automatic settings, and then also in time settings as far as dryer time settings go. And different heats. There's a high heat and a low heat. And we collected all this data and analyzed it to try to see if we could indicate when the clothes were dry based on these three parameters. If you notice, the fourth parameter we discussed, airflow, was left off, and the reason why is because we surmised that it was did not influence when the clothes were dry or not, so there was no need to even look at it anymore. But after doing all this testing and looking at the data, we couldn't figure out a good way to see when the clothes were dry. So we had to take a step back, and through some research, we figured out that if we calculated absolute humidity, that we could tell when the clothes were dry. So we came up with this formula through research and found this guy, Peter Mander. He's a chemist by trade, and he has a blog, and just through some research saw this formula, ran some numbers to compare it to a lookup table for temperature and relative humidity, because that's what's used to calculate absolute humidity, and ran some numbers through there, and through the range that we're going to use it, the formula was very accurate. Very pleased with that, so it worked really well. The units are grams per meter squared, and we're already collecting the relative humidity and temperature through those sensors. So we just collect those values, run it through an algorithm that calculates the absolute humidity, and it's worked really nice. So here you have the results. And the only difference is the absolute humidity is this purple one. So what happens was when your clothes first start, the absolute humidity is at X amount, whatever it is. A lot of that depends on, if it rained that day or not, whatever the absolute humidity is of the room when it starts. So you're going to see an exponential growth, and it's going to hold flat for a period of time, and then you're going to see a decay, and you're going to see some growth and decay. None of that really matters. What really matters is where you start at when you come back to it. So if you started at 5, say you start at 5 and you end back up at 5, when you end back up at 5, then you start a timer where the heat stays on for an additional 5 minutes. Once that 5 minutes is expired, you open up the relay that is providing the current for the heating element. Then you wait an additional 5 minutes, and then you open the relay that goes to the drum motor. So that totally turns off your dryer. And the reason that you do the heat, you turn it off after 5 minutes and then wait 5 minutes, is because you want your clothes to cool down. The reason why is to allow the wrinkles to come out, and also for safety reasons. You don't want to have clothes that have a lot of buttons or zippers that you're trying to pull out when they're still hot. Maybe a safety concern. So what we did is we implemented, like I said, the relays and to the test set that we designed, and that was our conceptual circuit. So ran some tests on our conceptual circuit, and what you see here is the mode, and you have 4 efficiency modes, and we compared it to 4 automatic modes. That's the comes with the dryer, the automatic setting on a dryer, and efficiency is the conceptual circuit running the drying cycle. So we have 2 different heats. We have high heat, low heat, 2 different loads, cotton and blended. We talked about that before. And we've calculated the total kilowatt hours for the dryer cycles, the cost of the cycles, and then also the time. And the total kilowatt difference, the cost difference, and the time savings. So if you notice, the efficiency modes all saved a tremendous amount of money. 12 cents, 9 cents, 14 cents, 16 cents. Average of 15 cents. per load. Time savings 36 minutes, 20 minutes 66, 51. So about 37 minutes, and that's a tremendous savings and time right there, because when you're washing clothes, or at least when I'm washing clothes, that the dryer is always the bottleneck. The clothes will finish washing, and then I'm waiting for the dryer to finish so I can load the next wet clothes into it that are already waiting. So, if I can save 30 minutes in doing that, 30 to 40 minutes in that range, that's a tremendous benefit for me. Takes the guesswork out of drying, and it saves, like I said, it saves power, which saves you money. 15 cents, you add that up over the course of a year. If you do 7 loads per week, then they can save you on the upwards of $50, depending on what your kilowatt hours are. It can save a tremendous amount of money through the course of the life of your dryer. So we took that conceptual design and the data we collected and decided that the concept was good enough to go forward for a prototype. And the prototype will be a standalone system. And that standalone system is what we refer to as the Clothing Dryer Efficiency Module, the CDEM. And the prototype consists of 2 parts. The first part is a miniature humidity/temperature sensor. And the temperature sensor indicates the dampness of the clothes. It is mounted in the dryer exhaust pipe, and there's a communication wire coming off the sensor which concatenates to a junction box. Now this junction box turns the power off to the heating element and to the drum motor via 2 different relays, and it calculates the absolute humidity of the temperature and relative humidity variables, and then the electronics programmatically calculates that. Same way that the conceptual circuit did it. Determines the leg of the heating element in the drum motor, and this can be done because the current consumed on the heating element is about 23 amps. But when the current cycles on and off, as you saw in the testing results data, it goes down to like 500 milliamps when the current's off. Now the leg that's on the drum is constantly consuming current. When the heating element's off, it's around 2.5 amps, 2 amps, to spin that motor that's spinning the drum. And your split phase system's set up to where you have 240 volts at 30 amps, and one leg is driving the heating element. That the one leg actually it shorts out. I mean, the current goes through there, and then your other leg is independently controlling the current to the drum motor. So you can tell which one is which. Like the case I just gave you, if the current drops to 500 milliamps, then you know that leg is your heating element. If it never goes below 2 amps, then you know that is your drum leg. So you can determine that by a current transformer and just monitoring the currents throughout the drying cycle. It compares the absolute humidity to the starting absolute humidity to the present absolute humidity. Same thing as conceptual circuit, where it starts, and when it comes back to that point, waits 5 minutes, cuts off the heating element, waits an additional 5 minutes, and then cuts off the drum motor. It also has a terminal block for the input and output of the 240 volts 30 amp power supply. It has a power cable on the output. This is the circuitry. Consists of a microcontroller, a Darlington pair array IC, current transformer, power supply, passive and active components, diodes for bridges to essentially change that current into a voltage, and a resistor for the voltage drop across to make that current and voltage. Just some additional circuits that we'll get into. Here's the prototype drawing. So you have your junction box here, here's your power cable, and then your power supply terminal and your dryer. You have a communication cable right here, and then you have your miniature temperature sensor right here. This is a block diagram of your hardware. You have your power supply, 12 volt and 5 volt, your current transformer, controller, relative humidity, and temperature sensor, relay driver, 2 relays, heat element, drum motor, and also a means to communicate with a PC if you wanted to. Prototype hardware schematic. Here you have your 5 volt rail, which supplies your temperature sensor and relative humidity sensor. It also supplies your microcontroller. And then your 12 volt power rail goes to your Darlington IC, which is driving your 2 coils for your 2 different relays. You have your current transformer right here. It goes across this resistor. Then there's a diode bridge and a cap and a resistor. And that's the circuit. And here's the actual picture of the prototype circuit. Proto board here. The higher voltage, I don't really want to call it high voltage, but the 240 30 amps is all on the top side, and then on the bottom side of this board contains all of the low voltage stuff, the 12 volt and 5 volt. So it's separated. And here's your relative humidity and temperature sensor, and then this is your cabling to your dryer, and then the power cord would land inside here on this terminal block. And here's your current transformer right here. A wire's threaded through there. So that is a picture of the hardware. And here we have the software configuration and variables. We just configure the microcontroller's pins. We have to configure one pin for the relative humidity and temperature sensor. It's a 1-wire serial protocol. We have one for your CT, which is an ADC, analog to digital converter. And then we have 3 pins that are configured for digital outputs, and those are to drive the Darlington pair ICs. And then we have an additional pin that's used to power on and off the micro through a transistor. Here we're declaring these variables. These variables, relative humidity, that's the temperature data that we read, or the relative humidity data that we read from the relative humidity and temperature sensor. The T is the temperature sensor data that we read from that same sensor. A is the absolute humidity calculation. The F is the first absolute humidity calculated that it stores. I is the raw current that it reads from the current transformer. U is the calibrated current that is read from the current transformer. And E is for your heat, O is for motor, I is for your loop increment, X is for your ADC loop. And then we initialize our variables, make them all 0 except for our X to turn on the ADC loop when it's going through that iteration. So it starts the program, it initializes the communication to the relative humidity and temperature sensor, that 1-wire serial. It reads R and H from the temp sensor. It calculates A from those values it stores F if it's the first iteration of the loop because it stores it the first time. Initialize the ADC, then it reads the ADC, and then it calculates the current based on that reading. And here what it's doing is it's making a decision, and if the current ever goes below 2, what we talked about earlier, then we know that that leg that it's on is the heating element. In that case, we'll make PB1 the heat, and we'll make PB2 the drum, and we'll make X0. So we don't have to read that ADC no more. We'll turn off that loop. If not, if the current does not go below 2, then it continues on. Now, at any point in time after the ADC and the reading of the relative humidity and temperature sensor and calculating the absolute humidity, if the absolute humidity is ever equal to what it was when it first started, then we wait 5 minutes, turn off E, wait 5 minutes, turn off O, and then we wait a minute and turn on E and O, and then we power off. So basically, that's what we talked about. If it starts out at X, comes back to X, the absolute humidity, it turns off the relay for the heating element, waits 5 minutes, then turns off the drum, and then the cycle's complete and you can get your close out. So that's the crux of the program. Here's our budget / bill. We've spent a total of $446. That includes the test set and also the prototype. We're not done yet. We may have to spend a little bit more money on maybe a PCB if we get that far, and more components. But right now, well within our budget. And safety provisions and standards that we're adhere to while performing this project. The prototype uses the built-in safety features of the dryer, which means that it's unintrusive. We didn't monkey with how the dryer operates. All we did is just be able to turn the current on and off to the dryer through the relays. The junction box protects the home from fires caused from electrical shorts. It's all contained. If there's a flashover or spark, it'll trip your breaker. So that's the safety concern there. We used insulated ring lungs, and that just provided more insulation, more dielectric strength to prevent, insulation degradation, flashovers, things of that nature. We used a 10 AWG wire to ensure the proper ampacity rating at 30 amps, and that is per the IEEE 835A, and that's the 2012 edition, and standard power cable ampacity ratings. We used a regulated power supply to protect all the integrated circuits, the Darlington pair, the microcontroller unit, to ensure that the voltages don't spike and that it's fused so that the currents won't exceed the rating. We used a 40 amp relay, which is 10 amps oversized to give us plenty of headroom. Max current drawn's 23 amps, so we're not even close. Approximately half of what it's rated for, so it's really good, robust design there. Spacing was concerned when laying out the prototype board, the proto board. So basically, what I iterated earlier is that everything that's high voltage is on one side of the proto board, and everything that's lower voltage is on the other side. So to prevent any flashovers or arcing there. And summary is, our prototype design was interdisciplinary between me and Jason. His skill set, my skill set, nicely paired with each other for this project. The design was data driven. We collected data, we did it the right way, made intelligent decisions on the design, and it works. We have we haven't tested our actual prototype yet, take that back, but the conceptual circuit works. We've tested that, so I don't think that's entirely fair to say that it works. So the future testing of the clothing dryer efficiency modules, what we talked about of the prototype, that's going to need to be done. And the project is on time and on budget, and that's because of planning, lean development practices, and lean procurement. And right now we're currently meeting the requirements and specifications of our project. So I'd like to thank you for your time and wish you all a good night.